In this article, we propose URPlanner, a universal paradigm for collision-free robotic manipulation planning based on deep reinforcement learning. URPlanner offers several advantages over existing approaches. It is platform agnostic and cost-effective in both training and deployment. The train policy can be applied directly to robots in simulators or the real world without requiring additional fine-tuning or the solution of inverse kinematics. URPlanner is implemented through the three main contributions of this paper. Firstly, we introduce an augmented policy exploration and evaluation algorithm, APE2, that can be applied to various DRL algorithms to enhance their performance. Secondly, we develop a parametrized task space and a universal obstacle avoidance reward that is independent of minimum distance. Lastly, we propose an expert data diffusion strategy, ED2, for efficient policy learning, which can produce a large-scale trajectory dataset from only a few expert demonstrations. As we compare the various motion planning algorithms from previous works, we find that although RRT and RRT star do not need training, their performance is highly unstable. This instability is attributed to the infinite inverse kinematic solutions for redundant manipulators and the inherent randomness of tree-based search processes. Although learning-based methods produce more optimal solutions, compared to traditional methods, a major drawback of learning-based methods is their high training cost. In contrast to the methods proposed in previous works, the two models developed using our URPlanner require only a few minutes for training and a few milliseconds for planning. This efficiency is achieved through the use of the proposed parametrized space and the minimum distance independent reward. In this experiment, we test the real-time planning capability of URPlanner. Initially, the robot arm transports a grasped object to a set drop-off position above the basket. Once the robot has reached the initial drop-off position, we then move the basket, and URPlanner is capable of replanning the motion trajectory in real time to follow the basket and drop the object into it. URPlanner can be applied to train a motion policy for any manipulator in different task scenarios of varying complexity. Our proposed method consistently performs better when benchmarked against other state-of-the-art planners. Training a DRL policy to handle all possible task scenarios is inherently challenging. Therefore, we introduce a policy library to enable our method to generalize effectively across various obstacle configurations. In the following example, the workspace on the desk is divided into three regions. Three sub-policies, each tailored to a respective workspace, are trained and stored in a policy library. Using this method, we present to the agent 6 new scenarios involving random obstacle and target layouts and show how it can retrieve the appropriate sub-policy from the library to generate collision-free motion trajectories. By approximating the surface of each cylinder that represents the robot's link using multiple line segments, we can significantly improve URPlanner's planning ability in constrained environments. In the following three scenarios, URPlanner effectively guides both the KUKA and Franka robot arms to navigate narrow spaces between the ground level and elevated obstacles. By incorporating the obstacle position into the state representation, URPlanner is capable of handling environments where the number and structure of the obstacles are known and fixed. In this example, the trained policy enables the robot to pass through the gap between the obstacles when space permits and to move over them when the passage is too narrow. By incorporating the occupancy grid into the state representation, URPlanner is capable of handling environments with randomized obstacle configurations. In the following scenarios, the robot successfully learns to navigate around obstacles whose number, size, and shape changes across episodes.